Okay, in this design example, okay, so that is the all the data given. So to center spacing in the longer dimension, that is 8 meter, means in the long side of the beam. Okay, here is the short of side of the beam of this beam. Okay, overall total length is more in this side, this is the shorter side. Okay, this span will be this one is the first span, this is the second span, and this is the third span. Okay, so there are three spans of 5 meter, 5 meter, 5 meter, and 5 meter, 3 at the rate 5 meter. Okay, so center to center spacing is 5 meter, and this beam is B2, B1. Okay, this is exterior beam, this one is interior beam, this one is also interior beam. Okay, and on the short side this is B3, 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 and the spots are 300 by 300 millimeter of columns. Okay, in this design example, design the interior long beam B1 of an office building. Okay, this is an office building, that is the B1. Okay, so here is the word mentioned, that is beam are not monolithic, means beams are disconnected at the ends, means they are not cast at this cast simultaneously, they are cast separately. Slab thickness is 160 millimeter. Floor finish, that is 75 millimeter of brick ballast. Okay, floor finish, that is 75 millimeter of brick ballast, 50 millimeter of PCC floor finishes. The beam B1 sports a 2 to 8 millimeter thick wall of 3 meter height, means this beam sports a wall also of 2 to 8 millimeter width and 3 meter height. With FC prime these, FY these, US size bars are to be used. Okay, in this example, US bars are to be used. Take width of the, definitely sports are of column, that is 300 millimeter by 300 millimeter. So take B that will be adjustable to sports, that is 300 millimeter. Design the beam for the following three options. First is the design with taking minimum depth obtained with the maximum steel ratio. This is the first criteria. Means first question option, design the beam with taking a depth that is against with the maximum steel ratio. Second criteria is take the depth equal to depth of the beam 835 millimeter and then design. Third is use depth of the beam 910 millimeter and then design the beam. Example 3.4, this is the same example I have discussed in the slides. Okay, in a slab system. Okay, the effective long dimension of the beam 8 meter, short dimension of the beam is 5 meter, slab thickness, brick ballast, each and everything is same. Okay, the first option is design with against minimum depth obtained with the maximum steel ratio, even if it violates the ACI minimum depth for deflection control. We have to design the beam against maximum steel ratio. Second is depth of the beam is 835 millimeter. Third, the depth of the beam is 910 millimeter. First of all, we will use the first option. Before using the first option, we will calculate the total load that is coming on the beam. Okay, so data given, length of the beam is 8 meter. Okay, so here, okay, that is the length of the beam. We are going to design this beam. Okay, not short beam, this is a long beam. Length of the beam is 8 meter. Slab thickness is 160 millimeter, and floor brick ballast, that is 75 millimeter. Floor finish 50 millimeter, FC prime 20 megapascal, FY 420 megapascal, and the width of the beam mentioned that you can use 300 millimeter. Okay, so first of all, slab load. So slab concrete slab thickness 160 millimeter divided by 1000 converted to meter, multiply with density of reinforced concrete. So answer is 384 kg per meter square. Then the brick ballast, that is 75 divided by 1000 multiplied by density of brick ballast. So answer is 135 kg per meter square. PCC plus Tarazu means plain cement concrete, that is floor finish, that is 50 divided by 1000 multiply with PCC density, that is 2300. So answer is 115 kg per meter square. So total dead load, that is from slab, that is 634 kg per meter square. Now the live load, okay, the live load that we consider for the design of office building. So we can use 250, 300, okay. That page number 115, we can go in the start, that is here, okay. For offices building, you can use the live load 250 to 425 kg per meter square, okay. So I will again go back the same page. Now coming back on the same page, okay, here is the live load, that is 250 kg per meter square. Now to get the total factor load, 1.2 dead plus 1.6 live. So 1.2 dead, that is 634, live is 250, 1.6 into live, okay. Then the whole is multiplied with 9.81 divided by 1000 to convert kg per meter square into kilonewton per meter square. Now on the B1, a brick wall is also resting. So brick wall width is 228 millimeter divided by 1000 to convert into meter, multiply with the height of the beam. Okay, that is 3 meter. That is the cross section of the wall. Then multiply with the density of the wall. To that the answer will be kg per meter square. Then multiply with 9.81 divided by 1000 to convert into kilonewton per meter. Okay. So service dead load from the brick wall, that is 12.95 kilonewton per meter. Okay. Then multiply this load with the to convert into factored load 1.2. The answer is 15.54 kilonewton per meter. Now the last the load, that is the self weight of the beam. Okay. So we do not know what will come the load after designing, even the width depth satisfy or not. Okay, first here is the approximate cell weight, that is the 2400 density of reinforced concrete multiplied with width of the beam and the height of the beam. Width, that is 300 millimeter, height will be L by 12. Okay, L is 8 meter divided by 12, multiply with 9.81 divided by 1000, the answer is 4.71. Then multiply with 1.2 to convert into factored dead load. Okay, so now the total load on the beam which we will design, that is 5.61 plus 15.54 plus 11. Okay, one thing remaining. Okay, this one is okay. This load, okay, that is in kilonewton per meter, that is kilonewton per meter square. Okay, that is the long beam. We have to calculate the equivalent width for the long beam. Okay, for this beam, okay, to get the equivalent width for this beam, for the long beam, the formula is 1 minus r square by 3 into Lx. Okay, Lx is the shorter dimension, Ly is the longer dimension. Okay, but r, that the ratio is shorter to longer. So 5 by 8, the answer is 0.625. The equivalent width is 1 minus 0.625 square divided by 3 multiply with Lx. Lx is 5. Okay, that is the formula we have proved in the previous slides. Okay, or in the previous lectures. Here we have just multiplied with 1.1. Why? When we design the interior beam, okay, we increase the equivalent width by 10%. Okay, so that's why multiply with 1.1. So the equivalent width is 4.78. Now we multiply this equivalent width, this total factor load of the slab, then we get the factor slab load on beam. Okay, equivalent width that we have calculated, that is 4.78 multiplied with the slab load. So the total slab load is 54.49 kilonewton per meter. Now the total factor load is WU, that is 54.49 plus 15.54 plus 5.65. So the total factor load is 75.68. Now we will calculate the moment for the simply supported beam omega L square by 8. Omega is 75.68, that is the UDL. L is the length of the beam. So the total factor bending moment is 605.44 kilonewton per meter. Okay, sorry, that is kilonewton meter into meter, not per meter. That is the moment. Now minimum effective depth for singly reinforced beam, that is mu over 0.205 into fc prime into b 702 millimeter, and the minimum steel ratio, that is 1.4 over fy, that is the minimum, and that is d minimum. Now depth for deflection control, that is minimum depth for beam for deflection control, that is L by 16. 8000 is the length divided by 16, the value is 500 millimeter. Okay, so the first condition is we have to these criteria we already know, these are the basic criteria, but the first condition of this question is you have to provide the depth of the beam against the rho maximum. Okay, so here is the rho maximum. The formula is 3 by 8 for the tension control, 0.85 into 0.85 20 by 420, that is the rho maximum value. Then with this rho maximum value you can get the value of depth. Okay, so you can put the value of rho max in this formula, that is the same formula we use for the getting the steel ratio for the beams. Okay, in this formula you put the value of rho here 0.0129 fc prime fy, all the values, d square, then you will take the d on the one side and rest of the items on the other side, then take the square root, you will get the same value of d 702 millimeter. You can use this formula or this formula. After getting the d, you multiply rho with bd. Rho is 0.0129, b is this, d is this. So area of steel is 2717 millimeter square. In this example, the author has mentioned you have to use the US customary bars. For the US bars, okay, these are SI bars. For US bars, you have to go at the start of the appendix of steel tables. That same steel tables are present at the end of the book. Okay, these are the bars you have to use, US customary bars. Okay, so the required area of steel, is 2717 millimeter square. Okay, so 25 1 bar area is 510 millimeter square. So you can provide 6 bars. Okay, the total area will be 3060 millimeter square, or you can choose different arrangements, means 4 number 510 bars or 2 number 387. You can use the alternate arrangements. Okay, here 6 number 25 bars, that area will be 3060 millimeter square, 12.6% higher. If we use 5 number 25 and 1 number 22, the area of steel will be 2937 millimeter square, 8.1% higher. So definitely we will go for second option, where the area of steel we have to provide less as per the requirements. Okay, the reinforcement details in the figure 3.21 is shown here. That is the part 1 of the question. The total depth will be 780 millimeter. Why 780 millimeter? That is 700 or 705 millimeter, you can do the round up. Then 75 millimeter for the double layer. Okay, so from center to end the total depth will be 780 millimeter. And hanger bars to number 3 13, and here 3 number 25 bar at the bottom, and the 2 number 25 plus 1 number 22. The all 3 bars are used for bent ups. Okay, so here is the detailing of the part 1 of the question. So now for the second part, okay, the requirement is use H 835 millimeter. Okay, the effective depth 835 minus 75 760 millimeter. D minimum, okay, that we have calculated in the previous, that is 702 millimeter. So our provided D is greater than 702 millimeter, so it is okay. The applied moment is here. So now I will use equation rho. Okay, so I will use the equation, the all the values 0.85 fc prime over fy, the exact formula 1.1 minus 2.614 mu 605.44 multiplied by 10 power 6 divided by fc prime b d square. Okay, in this example d is 760 square. Press equal, you will get the answer 0.0106. Okay, that is the same answer here, 0.016. You can use the exact formula. Okay, do not need to calculate the omega r. You will put all the parameters and get the rho that is greater than rho minimum. Okay, and rho maximum value is okay 0.0129. Okay, that is greater. So our provided steel is greater than rho minimum and less than rho maximum, so that is okay. So that is the method 1. Now for area of steel rho bd. Okay, so 300 into 760, answer is 2428 millimeter square, and the bars provided are 4 number 22 and 2 number 25 will be sufficient. The area of steel is 2568 millimeter square. Okay, you can see from here. This is US customary reinforcing bars. Okay, here are in the first column that are in SI, means in millimeter, 10 millimeter, 13 millimeter bar, 16 millimeter bar. Here same bars with in the FPS units, that is number 3 bar, number 4 half inch dia, 1 inch dia, that is 25 millimeter. Okay, so here are the areas, here is the diameter, and here is the nominal mass, mean kg per meter. So you can verify the 4 number 25 and 2 number 25 will be sufficient. Now method 2. In the method 2, you need to only calculate mu over bd square. Okay, mu over bd square. Here you need to calculate only this value in the method 2 and method 3. Method 2 is the table, method 3 is the curves. Okay, and here are mu over bd square. You know the mu value, you know the value of b and d square. Okay, after getting the value of r, you will go at the end of the book in the design aids. Okay, here moment capacity of rectangular sections. Okay, what value you see, that is 3.494. 3.494. The fc prime is 20, fy is 420. Sorry. Okay, fy 420, fc prime 20. So again let's see the value, that is 3.94. okay, 3.94. okay, here 3.91 and 3.98. so we will pick the higher reinforcement ratio value. So we will round up, or we can interpolate between these values. So we will pick 0.0125. okay, 0.0 by approximate interpolations. Okay, you will get the value of 0.0108. okay, between 3.91, sorry, I think I'm making mistake, 3.49. okay, not 3.9, means near to 3.5. Here 3.49 3.44 and 3.54. So you will get, after getting the interpolation, you will get the value for 3.49. Okay, that will come between these two values. So that's how we use the tables. That is the second method. In the third method, we will use the mu over bd square value by using curves. Okay, the curves also given at the end of design charts here. 20 megapascal. Okay, and fy are given. We will select the fy, our own curve. So our value is 3.49. Let's take it 3.5. So 3.5, that is for 20 curve. Third one comes here. Okay, after coming here, we will come on this same straight line. Here we will come here. Okay, that is again 0.01. Okay, by interpolating that is 15, so that will again become near to 0.0106 or 7. Okay, so that is from the value of mu over bd square. So that is the third method by using design curves. Okay, now the fourth method, that is the trial method. Okay, assume a d by 3, that is equal to 253 millimeter area of steel. And from the assume a, you will get the area of steel. Okay, you have all the values, you will put the a, you will get the area of steel 2528 millimeter square. Then the second trial, you will get the new value of a from the area of steel from the first trial. Then here is the a new value 208 millimeter. Then you will put the a value in the again previous equation as, you will get the as new value, that is 2442 millimeter square. Then again you will calculate the a value. The new value of a is 201 millimeter. The new value will come from the previous area of steel. Then again you will put the a value in this previous equation of area of steel. Now you can see 2429 and 2442 are nearable. Okay, sufficiently close to previous answer. So you can select the 2429 millimeter square. So almost the same reinforcement is obtained as in the first method shown in the figure 3.22. So these are all four methods. Okay, here are the uh, detailing is shown. So at the bottom, 2 number 25 plus 1 number 22, and in the second layer 3 number 25, and the gap between two layers is 1 inch, that is 25 millimeter. The ties again assume we didn't perform the shear analysis, we perform on the bending analysis. And the hanger bars you can use either 2 number 10, okay, number 13, okay, either. That not important in the singly reinforced beam. The top bars are important in the doubly reinforced beam. That is our next topic. Okay, that is the second method, second question statement. Now the third question statement is here. Now the third question statement is use H 910 millimeter. D is 910 minus 75, 835 millimeter. In the third question statement, it is mentioned that use uh, 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 perform the design using trial method. So A D by 3. Okay, get the AS, all the parameters you have MU, D, FY, and you will put the A, assume A, you get the area of steel. Okay, so then in the second trial you will again calculate the A from the previous area of steel, that is 2301 millimeter square into Fy, okay, divided by 0.85 Fc prime Fy. The A value is 190 millimeter. Then you will put in the equation again, get the area of steel. Area of steel value is 2164 millimeter square. In this equation only A is different. So now you will again calculate the value of A. The value of A is 178 millimeter. Okay, so after getting the new A value, get the area of steel value also. Okay, you can see only A is changed. So the value of previous answer is nearable. Okay, after three trials are enough, you will get the same answer from the previous trial. So the area of steel is provided is 5 number 22 plus 1 number 19 gives 2219 millimeter scale as shown in this figure. Okay, 3 number 22 bottom, 2 number 22 plus 1 number 19 will be used as a bent up. Okay, here. Now the last part is the make the bar bending schedule. Okay, so bar bending schedule I have discussed uh, in the previous lecture. So the bar bending schedule I will left on to you. Okay, so that's all for today's lecture. Have a nice day.